Okay, so hello everyone. This is a demo video for the Digilent analog discovery board. So what you are seeing on the screen is basically the interface software for the provided Digilent board, and this would interface with the signals with the actual board in real time. So we would be able to send in commands and observe the corresponding outputs within real time. So to test an application on this waveform software for the Digilent board, I would be using ADC tracking lab, in which we would be using CD4029B CMOS up and down counter. So this up and down counter is primarily used to create a 4-bit ADC, as you can see here, and it is done so using a weighted resistive network instead of R2R ladder, which would be implemented with another IC or a combination of two of them. But for this demo, I'm only implementing the uh, single IC CD4029 resistive network divider in order to create a 4-bit design. So the specification of this IC can be set from the datasheet itself. The datasheet provides the configuration mode for each of the provided pin as to decide which configuration or which mode we need the IC to operate in. For example, we want the IC to we want each of the bits to increment with the clock positive edge, and for that we need to set the carry in and preset enable to low. So both of these pin on the circuit that you are seeing on the corner is set to low. And similarly, we want our counter to operate in the up mode, and also in the binary configuration. So both of these pin 9 and 10 are set in high configuration. um, if I could zoom in on the data pin, yeah. So as I told you, preset enable and carry in were set to low in order to obtain an increment from the positive transition up and down. um, Pin 9 and pin 10 were set to high in order to obtain the binary mode in a configuration, and Q1, Q2, Q3 and Q4 would correspond to each of the pins connected to the resistive network as shown in the figure 1 of the design here. Similarly, jam 1, 2, 3 and 4 would be left floating as we do not need to use them at the moment, and VSS has to be grounded in it. VDD would be provided with a 5-port DC, and the clock would be provided from the generator itself from this waveform software at the frequency of 1 kilohertz, and with the 50% duty cycle, and the rest of the settings I would show you later on. Right, and the output would essentially be the common terminal on which these resistive network would be shorted, and we would be taking the measurements in the voltage mode, as you can see in the figure 1b, instead of the current mode, because of in order to basically protect the circuit as it is being powered by the computer board itself. It is entirely possible to do that as well, to use the figure 1a and take measurement from current. But just to be on the safe side, when we are using the waveform software with the Digilent board, it's better or advisable to use the voltage mode as in shown in figure 1b. Okay, so these were the configuration for this IC, and it is operated at 5-port DC, and the rest of the data sheet basically deals with further designing and application. So this figure 10 is quite important because it essentially shows how each of the output would correspond to the provided input clock. And as you can see, Q1, Q2, Q3 and Q4 are essentially increased by the power of 2 and as compared to the clock provided. So we only need to control the clock in order to generate the corresponding bits for the ADC. Right, so this is it for the design part, because at the moment we are only using the resistive network and not the R2R ladder network, this one. Also for these 4 values, the actual values would be used instead of the nominal ones that are calculated for R1, R2, R3, R4. So there is some error expected, but hopefully it wouldn't affect our measurement significantly. Okay, so what we are expecting is to have an output of this sort as shown in figure 5. As you can see, it is similar to what the output that was provided in the data sheet. We would be providing it a clock from the function generator, and the corresponding bits Q1, Q2, Q3, and Q4 can be observed on the oscilloscope. And corresponding to these 4 bits, essentially we are obtaining a analog output, as you can see in the same figure 5. Obviously you can see the steps because we are only using 4 bits so that's total of 16 steps, but it can be increased by cascading multiple 40229 ICs. But for this demo, I just have mounted a single IC, as you can see in the circuit, and let us see the output from it. So there are a couple of things that we would be observing from our circuit, including nonlinearity and glitches by inputting capacitor to each of the MSP, and yeah. So this wouldn't be the part of this lab. So let us see what we can do in the waveforms. Okay, so and this is the waveform software that Digilent provides. It contains multitudes of function. Obviously it has its limitation because it's working at low power of only 5 volts provided by the PC USB port. So but it's sufficient to discover and study the ADC tracking behavior. So primarily I have provided a supply voltage of 5 volt, and that can be controlled using these slider switches or this drop down menu from here. And the analog discovery board can provide both positive 5 volts and negative 5 volts, so depending upon our application. For example, if we are using a op amp in order to amplify the output from the resistive network, then we would have to power it using both of these supplies. But for now I'm just powering the IC itself, so this positive VDD should be sufficient. Master enable is responsible for turning on or off both the power supplies at the same time, and the tracking here would essentially ensure synchronization between the positive VDD and the negative VDD. At the same time, we can monitor the USB port as to keep the conditions safe and ensure that the circuit doesn't draw too much of a current and ends up destroying the USB port. Right, so other than the supply voltage, I'm using waveform generator in order to provide the clock cycle. So we can control the waveform from this drop down of the type right here. At the moment I want to provide a simple clock with 50% duty cycle, and the amplitude can be selected from here, from this drop down. For this demo, I'm not going to set an exact 5 volt because of the limitation of the USB port. So let us first see what output we obtain from 1 volt, and then we can maybe um, increase the voltage amplitude on the offset. So I'm using the offset because I want my voltage to be above 0 volts, and don't want it because IC essentially wouldn't read the negative voltages. Okay, so this would be the square waveform. Oh, sorry. And this is the scope. So in the blue, I believe it is the sorry. So okay, so this is from the previous output. If I run it now, so the output clock waveform appears on the scope. The scope offers various options in order to take measurements and to see the exact values using different cursors for the rise time, fall time, the duty cycle, time period, frequency, the voltage in RMS and peak to peak. and most of the options that are provided that would be provided on an actual oscilloscope. So this waveform that you are seeing on the screen is the input clock, and the output is obtained uh, in the blue, but it's not quite apparent because we set the voltage at 1 volt, so therefore the output is nothing but a DC signal, but it can be improved. So we will try to do that later on. Another option that I wanted to show here was of this voltmeter. So on both of the oscilloscope channels that I'm using, we can see the RMS value in real time, as shown here um, by these two indicators. Right, so I would stop this video here, and I would hopefully tune the input waveform from the function generator to the point where we are able to clearly observe the output in the blue here, so as to see how the tracking ADC is working. Ideally, what we should be getting is a waveform that looks something like this. From the 4-bit ADC, we should be able to generate a sawtooth wave, as shown in figure 5, um, for which the circuit is correct, but the input waveform that we are providing through the clock is not. So I would tune that and would probably make another video in which I would explain how we have obtained this waveform. Lastly, I want to show an actual result that is obtained from a real oscilloscope instead of the waveform. And you can see here that the clock that was provided was at 1 kilohertz in this image, at the peak to peak voltage of roughly 5 volts, which should be at least equal to or less than the VDD that we provide. And you can see the corresponding ADC that is obtained. It has total of 16 steps corresponding to the 4 bits that was provided by the 4029 IC. In the next video, I'll probably try to replicate the results on the waveform of this waveform software of the Digilent board. But for now, this is it.